Okay, we will go ahead and get started. Good morning, everybody. Welcome back, or welcome to the Institute. We are very happy to see so many people interested in this program, and we are very excited to have a chance to spend another week with all of you. My name is Vitek. I am a faculty in the College of Computer Sciences, Curie College, it's a new name of Computer Sciences at Northeastern University, and I'm one of the co-organizers. So before we start, we have some, especially for those of you who are just joining us for the first time, we have some logistics. You probably have already seen the Wi-Fi password. We also have on the whiteboard the URL for Piazza. So Piazza is a discussion board. It allows us to share materials and also post questions and answers for everybody who participates in the Institute. And it has many useful links, including the link on the Google Drive or on GitHub for the materials. So all the slides and handouts that we have, they're all available. So look at this link or also at links posted on Piazza. So we have a notice of filming. We occasionally have photos. We have a college photographer also comes to take photos for the newsletter. If you do not want to be on a photo, please let me or any of the group members know. We take this very seriously. We will make sure we are excluded from every photo that we take. And let's see, a couple more things. We'll have refreshments at 10:30. However, lunch is on your own. There are many places. The Dunkin' Donuts is open now. We have Ruggles and also Cross Huntington. There are many lunch places. However, if you would like to stay here for the lunch hour and work, or just kind of stay quiet, we also have one more option. You can order online your lunch in B-Boots, and our group members will come and give it to you here. So if you look on Piazza, there is a foodies list post, so it has the information on how to order this and how to add your name to the list of those who need to be picked up. So you will pay yourself, but we'll bring it to you here. And tomorrow we will have a participants dinner, and you are most welcome to join us. For those who were here last week, it will be in the same location as last week. It's a 20-minute walk, or very short sea ride or Uber ride from here. What is different from last week is that before we go to the dinner, we will actually have a poster session where each of you will present a poster on your research. I will say no more, but you don't need to worry about this right now. So, but make sure you are psychologically prepared to speak about your research around 4 p.m. tomorrow. So I think this is all I have to say about the plans. So let me actually introduce also Mina, who is sitting in the back. Mina is one of the co-organizers, and she will be leading all the hands-on part as well. So if you have any questions, please reach out to Mina and me, and we'll have many other group members who will introduce them as we go as well. Okay, so let's go ahead and start. So what I would like to do today is to talk about statistical methods which are specific for relative protein quantification for mass spectrometry. Those of you who were here last week, you know that we spent a lot of time talking about statistical methods in general, right? Just basic methods and how this works and so on. We didn't really talk about the specifics of quantitative mass spectrometry experiments. So today is the day when we start doing this. And before I move on, I want to say that I will be talking about MS-STATS. This is the tool which is developed in my lab. And the work is getting close to 10 years old now. I mean, it started 10 years ago, and it has been a contribution from a large number of group members. And I really want to acknowledge everybody before I start. So Mina is the lead developer and the leader of the project in MS-STATS. Cyril Errol, Sicheng Ting, Sarah, and Sung Heng are current or very recent group members who contributed a lot to this work. And Vivian Team were my PhD students way back at Purdue, almost 10 years ago, who were at the origin of this project. Okay, so first thing I will do, I know we have roughly half of the people here who were not here last week, so I would like to do two things. I would like to briefly remind you what our objective is, and also I would like to introduce a data set that you will be looking at during these 2.5 days. So some of you have seen this. I apologize to make sure that everybody is on the same page. So the first thing, we need to make sure that we can distinguish random variation in our data, which can be due to different sources, such as technical, instrumental, signal processing, or biological variation, from the systematic signals which are introduced by stresses, disease, or whatever condition we're interested in. So an important aspect of statistical analysis and experimental design and statistical methods development is to understand what are the sources of variation which are present in our experiment, which of the sources are nuisance which we want to either minimize or otherwise account for, and which are the sources of variation which we're actually interested in, and how can we distinguish them. And so the reason why we need to do that, and the reason why we need statistical methods, is because doing this allows us to conduct research which is objective, so it is not affected by our preferences or subjective judgment, and it is also reproducible. And an important thing we talked about last week is the fact that reproducibility is not one thing, it's actually a spectrum. So on one end of the spectrum, we have research which is publication only. When you write a paper, nobody can do anything, and repeat what you've done. And then we have a whole spectrum where we need to be able to repeat exactly the same analysis of the same data which you published. So you should be able to take a paper and reproduce everything from the raw data and get exactly the same numbers back. Then reproducible data analysis talks about the fact that there's more than one reasonable way to analyze a data set or work with the problem. And so, of course, this will not give us exactly the same numbers, but qualitatively we should obtain the same conclusions if the multiple methods are equally reasonable. And the reason for that is that we don't want our conclusions to depend on the small, tiny decisions on tuning parameters, on little choices, which have to be made, but they're not really critical to our project. So we should be able to reproduce this with multiple methods. And then, of course, we want to be able to reacquire the data from the same biological samples and obtain qualitatively the same conclusions. And the gold standard is that we want to take new biological material from the same population, new subjects, for example, and repeat the whole workflow and obtain qualitatively the same conclusions. And so what I would like to talk about today and tomorrow is these two parts. So how can we make sure that we have data analysis which is repeatable and reproducible? What we did last week, we talked about these parts a lot. So how do we design the experiments to minimize deficiencies, to minimize biases? So, the first thing is I would like to illustrate the difficulty of that and the challenge with the example which some of you have heard already last week. So one more thing. Also another thing we did last week, we talked about different goals of statistical analysis. So we can do class discovery, where we discover groups of subjects or group of proteins which are similar to each other. We do class comparison, where we compare the averages of protein abundances between conditions. And then we do class prediction, which is important for biomarker discovery. So what I will do today, I will focus on statistical goal number 2, where we want to know, on average between the subjects, is there a change in protein abundance? And so the methods we discussed last week, these were t-test, analysis of variance, and there can be other methods. Many people brought up non-parametric tests like Mann-Whitney test or something like that. So these will be all the methods which are appropriate for comparing average protein abundances in different conditions. Okay, so now to illustrate the challenge of that, this is the study by the Association of Biomedical Resource Facilities, where Mina and I were involved. So this is the organization which brings together people who work in core facilities. And their objective is not necessarily, to develop new and cutting-edge research, but rather make sure that they have good quality procedures so that they can analyze samples from their collaborators in a way which is reliable and reasonable. And so what they do for that, they create studies where each member of this organization analyzes the samples or the data in a way that they're used to, and then they compare the results. And again, it's not a competition, they just try to establish good procedures. And so this particular study was specifically focusing on statistical methods for detecting differentially abundant proteins from data which are already collected. And so to make sure that we can decide which way of proceeding is better than another, we need to have a situation where we know the ground truth. We know what's the right answer, what's the wrong answer. So for that, we designed a controlled mixture, which looks like that. So there is a yeast printing digest as a background. And in this background, we spiked several proteins, 1, 2, 3, 4, 5, 6 proteins in varying concentrations. And we acquired data from these 4 conditions in 3 replicates, so it's 12 runs total. And the goal for the participants was to take this data and to tell us which proteins are changing in abundance. So the spiked proteins, we obscured them, we gave them IDs which were in the database, which were very much like yeast IDs. So this was acquired on a thermal instrument, in DDA on an Orbitrap. And then from this point on, we gave the participants several choices. They could take the raw data as they come out of the instrument and they could use their favorite workflow, or we searched the DDA spectra using a database search software, and we provided the IDs which they could take as an input. Or even more, in addition, we also did the MS1 quantification with Skyline, and we also made this available. So the participants could choose if they focus from the whole pipeline, or they just start from the partly processed data or fully processed data. And they had to fill in the questionnaire where they say, 1, what was the statistical analysis that they used, and 2, which proteins are changing in abundance. So they were supposed to report differentially abundant proteins for each pair of the 4 conditions. And so our work was to evaluate what they did and to decide which of them were better than others. So this was the result of the submissions. So here we have this. So the x-axis here is the identifier of the group who submitted the results. It was double-blinded. We don't know who they are. They didn't know who we are, at least in the beginning. So here we have 3 groups. So this is the group who quantified proteins based on the peak intensity. This group did counting of an SMS spectra. This group did something hybrid. This group didn't document what they did. The colors correspond to their inputs. So the yellow color means they took as input the very raw data. Darker, very raw, but they kind of cross-checked with our results. And then peptide IDs, or they took Skyline output as their input. So here the y-axis is the number of proteins which were reported total in their study. And you see already that there is quite a bit of difference in the number of quantified proteins reported by the participants. So this horizontal line corresponds to what we found. And so those who took our data as input, they had the same number of proteins. Others had either less or they had more. These guys misunderstood the instructions, only reported differentially abundant proteins. So human error, you know, that's the thing, right? So we have a lot of that. So, okay, so there's already some diversity, but this was not really the objective of the study. We were interested in relative quantification. So we want to know how successful were the participants in detecting differentially abundant proteins. So here is a similar figure. So each panel here corresponds to either intensity or spectral counting, hybrid, whatever they decided to do, and we don't know what. And below the horizontal line, the numbers are the number of true positive changes in protein abundant in the pairs of conditions reported by each study. So 36 is the maximum. Okay, so you see below the horizontal line that, well, there was some variability between the submissions. More importantly, above the horizontal line, this is the number of false positives. And you see the tremendous amount of variation that there is between submissions. So this group did reasonably well. They had a little bit of false positives. This group did really, really poorly. So here we have 2,000 differentially abundant proteins by someone. This one has 700 differentially abundant proteins. So clearly, there's a lot of discrepancy between them. And remember, these are core facilities. These are people who do this, you know, regularly, right? So, well, what happened? So we also asked the participants to report the fold changes of differential abundance between conditions. So now here we plot on the log scale the fold changes, but only among the background proteins. So we removed proteins which we know are differentially abundant. And the x-axis here is the same, the order of the submissions is the same as in the previous plot. And so you see that there's quite a bit of variation in the fold changes between different proteins. And this happens for everybody. So every group, every submitter reported substantial amount of variation between conditions. But the difference is that this group was not misled by this variation in the fold changes, and they could distinguish systematic changes from random artifacts. Whereas this group clearly was misled by some of this variation, and they reported this as systematic changes in the patterns. And so this illustrates the challenge. And this, by the way, happens regardless of which method they use, right? So spectral counting or some hybrid method, so it doesn't matter what method you use. So we looked into this a little bit more. So we tried to parse the questionnaire that people submitted in terms of, what they did. Okay, this is the input data. So here, each row is a submission. The column is what was used for input, how they identified the spectra, how they quantified the peaks, summarized statistical inference, multiple testing, and so on. And we used different colors for, some kind of patterns in terms of tools they used and so on. We didn't find any patterns. I don't know, maybe you see something. Well, clearly there's something going on with the multiple testing correction, right? But other than that, we didn't find any patterns. So really the main point of this figure is that there are many colors in this figure. So there are many ways to go about this problem, and different groups chose different ways. And so you see that there is not really any row which has exactly the same identical procedure everywhere. So there's a lot of diversity. This is unfortunately the state of the art for the moment, that many people have many opinions on kind of how to do this. Now, in terms of performance, we tried to group this, well, for lack of better ideas, we group this by positive predictive values. So this is the proportion of changes among the reported changes. So if we didn't detect something true changing, fine, but if we claim that something is changing, how likely is that it's actually true? And so this group has positive predictive value 70% or higher, so this we say is reasonable. This is between 20 and 70%, it's not great. Below 20% is really high. So this really what we found, right, that there are many ways of going about this problem, and there is a lot of discrepancy in performance. We found one thing though. Oh, so before that, so of course when we did all of that, many people were saying, okay, so well, is there a tool that does better than another tool? I did Max want to do better because I want to know that. And of course we looked into that, and in fact, participants were allowed to submit multiple analyses with multiple tools, whatever they wanted to do. And so here, for example, are two groups which look into Max 1 and Perseus. These groups did well, and these groups didn't do as well. These are the groups which use Skyline and linear modeling in R. This did well, this didn't do very well. Now, also some groups compared peak intensity versus spectral counting. So this group found that peak intensity and spectral count did equally well. This group found that one was much worse than the other. So choosing the workflows, we have discrepancies in conclusions. And so the only thing we really learned from that was this. So here, this column is the identifier of the lab who submitted the analysis. So what I'm doing here, I'm circling the submissions from the same lab. And so what you see is that with one exception, this submission will cross this line. So it means that the labs who know what they're doing, they can use multiple tools and do it well. And the labs that need to gain more expertise, they can use multiple tools, but switching one tool to another will not necessarily. So it's really about the user expertise and the understanding of the tool and understanding what are the steps and what are the assumptions and how to work with this. And this really was one of the reasons why that motivated us to create this program. Because we realized that it's not only about putting the tools out, developing the tools and making it open source and available. It's really important, but this is not enough. We really need to understand the reasons why the tools make certain decisions and what are the assumptions behind them and how we can work with this. So this study was published here. If you are interested, you can look at that. But most importantly, you will be actually working with this data for the hands-on for the next 2.5 days. So this was the reason why we discuss them. Okay, so now, well, first of all, do you have any questions? Or comments? Yes.
Were all of the parameters the same for each group when you searched with different tools? With all the parent?
You know, it is hard to say. It was definitely the same for us when we searched that. But in terms of submissions, what we also found is like, besides all of these difficulties, documenting the workflows was really a challenge for many participants. So some would just skip steps. Some would just say, like things, for example, yeah, I used R. You know, like, or some like in-house software. What do we know, right? And sometimes also noticed that they were answering questions which were not quite answering what was asked. And this made us think that probably the person didn't quite know what was going on, you know. So there's a little bit of everything. So it was very, very difficult actually to parse this questionnaire because there was so much diversity. So, okay. So now let's talk about MSTAT. So between now and the end of this hour, I will talk about the way we see this and how we approach this problem and the tools that our group makes available. So it started a long time ago as part of a collaboration with the Abersold Lab at ETH, where one of the group members was interested in studying breast cancer cell lines. This is the low invasive and high invasive cell lines. And the cell lines were subjected to low oxygen versus regular oxygen, and the duration of exposure was different, 6 or 24 hours, and there were multiple cell cultures, and then there were also multiple enrichment steps, and then there were multiple mass spectrometry runs for each enrichment sample. And so there were many different conditions and many different replicates, and the question was, well, what is the effect of these conditions on the protein abundance? So this particular data set was acquired in label-free DDA, and this is one protein from this data set. Here, the x-axis is the combination of cell line, oxygen exposure, and duration. Each color corresponds to a LCMS feature, so a peptide ion. Each dot is the replicate across multiple, cell cultures and enrichments and technical mass spectrometry runs, and the lines link the means of these replicates for this peptide. And so the question that this colleague was asking is not just, okay, what's changing between one cell line versus the other, but there are more complicated questions, such as, is the effect of oxygen exposure on protein abundance in this cell line the same as the effect of oxygen exposure in this cell line? And so the way she approached this at that time was essentially she would separately align LCMS rights for each pair of runs and would try to somehow find these peaks and then put them in Excel and then do some t-test. And I had the feeling that it's got to be better than that. And there are many reasons for this. So one reason is that we have clearly differences between different peptide ions. So between low and high invasive, clearly there's some regulation going on. But now if we want to know between different oxygen exposure, there is some disagreement between different peptide ions, so how do we handle this? There are missing values. What we also talked about last week is that we have many conditions, even if we want to compare a subset of conditions. There are many conditions that are informative of the overall variation. We should be able to use this to be more effective in estimating what the variation is. And so this was at the very origin of our work with MSTATs. So since then, it evolved in a very large project. So by now, MSTATs is actually not even an R package. It's a collection of R packages. So it's a family of things. So it is R-based open source tool for quantitative proteomics. The main question that we answer, but there are many others there as well, is which proteins change in abundance. So we are interested in experiments which have complex designs, not just two conditions, although we can do this as well, but it's more about factorial experiments, paired designs, time course, and the reason for working with that is that, well, it can be more informative in many cases, but also all of these experimental designs that require statistical models which are specialized for that design. And how can we make it available in a way which is general and automatable. And we can also summarize the abundance of a protein in each subject across all the features and so on a relative scale, which is comparable between the runs. And this is useful, for example, if you want to do class discovery, heat maps, clustering, and so on. It is also useful if you want to do class prediction, biomarker discovery, etc. It started with label-free. So we work with what Brendan would call chromatography-based quantification, Brendan McLean, who is the developer of Skyline. So we can quantify spectrum with DDA, DIA, PRM, or targeted SRM with or without labeled references. More recently, we started working with experiments which are other than that. So we have MS-stats TFT. You will have a chance to look into that a little bit, I believe, tomorrow. And also, more recently, we have work which extends beyond just protein quantification, in particular, looking for differential post-translational modifications and so on. We have multiple functionalities, so data visualization, we really believe we need to look at the data. Statistical modeling and inference, system suitability, quality control, assay characterization. I hope to have a chance to talk about this tomorrow. And sample size for testing and classification. As I mentioned last week, when we analyze a data set, we immediately view it as a pilot study for the next step. And we can learn various components from that, withdrawal power curves, or help with the simulations. Now, the input to MS-stats is a report which would be produced by a data processing tool such as Skyline or OpenMS or many others. We don't do that because there are many smart people who put a lot of effort into that and they do it better than we do. So we just work with them to have the report read into R. We're trying to be as inclusive as possible. So we work with the major tools which are out there, so including MaxQuant, SpectraNote, Protein Discover, and so on. So some of the tools export, such as Skyline or OpenMS, they export reports in the MS-stats format directly. Other tools, we just use their output and we write converters so that it's converted to our tools. So that's really the status. So, okay, so what do we actually do? This is how we see the whole workflow of analyzing, actually designing and analyzing an experiment in quantitative proteomics. There's a lot that has to happen before we actually collect the data, making sure that our assay is actually performing as we would like it to perform to actually be able to measure things. System suitability, making sure that our measurement system is working as needed. Experimental design, we talked about this a lot last week. And then after the data are collected, we need to do data processing, statistical analysis, and then learn from this to help design a subsequent experiment in terms of sample size, and so on. So I will focus on this part today, and hopefully tomorrow we can do additional things as well. So experimental design, we talked about this a lot. Let me just say that we need to first actually convince ourselves that class comparison is what we're interested in. Right? That we want to compare averages as opposed to do biomarker discovery and so on. That's important. We need to make sure that we select the right conditions, we define the right populations, that our subjects are representative of the underlying populations, and that we have enough replicates. And then we also need to think through the technological aspects such as sample spread, enrichment, fractionation, and so on, how to acquire the data, and of course randomize. And again, I hope by now I don't need to convince you, but I'm still surprised how often people forget. So make sure that this happens. Okay, so in terms of complex design, so well, this is one example of complex design that I just described, but we can also do other things, which, for example, are combinations of group comparison and the time course experiment. So, for example, here, it was a study also some time ago which was in collaboration with clinicians who studied osteosarcoma. It's a childhood bone cancer. And they had some number of subjects who are healthy who came to the clinic, like for an eye exam or something like that. They had the blood plasma for them. And then they also had 14 subjects which were diagnosed with the disease before treatment. Then they had collected samples in time at different stages through chemotherapy, before surgery, then also after surgery, and then they also had additional follow-up samples sometime later. So this design is a combination of group comparison design in the time course, and we can ask questions such as which proteins are changing in abundance between healthy and disease diagnosed, which proteins are different at diagnosis, but then with time they go back to the regular levels after treatment, and so on. So this would require specialized models which need to account for the fact that we look at the same subjects in time, but it also has some other subjects which are controls. And so MSTATs can do that. So in terms of data processing, as I mentioned earlier, we try to be equal opportunity offenders, and we take any tool we can work with, and we try to do a good job parsing their outputs and understanding what the tools mean. In some cases, it actually requires us to go to a fairly low-level output files. For example, Max Quant will have to take some of the intermediate data files for input to MSTATs as opposed to some kind of very last sum very fine. And then, in terms of data processing, we would need to, of course, visualize the data, do quality control, normalize, and so on. And let me just spend a little bit of time on that. So this is the example of the input to MSTAT. So it's essentially like an Excel spreadsheet or tabular format. Here, one line corresponds to one LCMS peak in one run. And we would have protein name, peptide sequence, charge, fragment, and so on, the replicate, the run, and the intensity on the original scale. An important convention, you will have time to practice that, is that each biological replicate has to have a unique identifier. This way we can distinguish experiments which have distinct group versus time course. Because if we have a same biological identifier present in multiple conditions, then we know that this is either a paired design or a time course, and we will work with that differently. So setting up the identifiers is one of the common challenges. So you will have an opportunity to practice that. And so after we converted the reports, we also do filtering steps, and there are many. For example, we can do Q-value filtering. So Q-value is essentially measures the confidence in the identification, for example, for DDA or for DIA. And you can have choices such as just removing this particular feature from the run, or if you remove too many of these features across multiple runs, remove everything. And I will talk at the end today, hopefully, how this affects the results. And
ask you a question?
Yes, please.
When you say feature, what do you mean right now?
Sorry?
You said you want to remove, or you mentioned the possibility to remove certain features. What exactly do you mean by feature? A quantitative liquid chromatography signal, or some mass spec fragment thing?
So, right. So I define the feature as a peptide ion, so essentially a peak in the LCMS retention time versus MO space, right? Across all the runs.
Yeah.
And so when I'm saying filtering, well, so it depends how, because we work with different tools, right? Different tools make different decisions. You can have, for example, a situation where you have this peak aligned across multiple runs. In run 1, you have really bad Q value. In run 2, you have good Q value, right? And so it kind of made its way to the report for that reason.
Okay.
And so now, well, what do you do? Option 1, you just keep it as is, right? Option 2, you say, in run 1, I remove this and make it NA because it's a bad Q value. Option 3, I remove the whole thing, right? And so that's a decision, and we will discuss a little bit here, but especially in the capstone towards the end of the week, we will talk about this. So, okay, so, but there is some work that has to happen before that. So for the moment, let's just say we take whatever is given, right? And we will go with that. We will come back to that. So what I would like to focus on right now is normalization. Because I would say that this is probably among the most challenging steps. And in our experience, when we work with the collaborators, this is where most of our time goes. Trying to understand, okay, what are the signals that are systematic but nuisance signals, which we can somehow account for before doing the statistical analysis. So here's one example. So this is a plot that MSTATs would generate. So the x-axis is the run. So the runs will be randomized, but now we ordered them such that vertical lines separate the conditions. So we have 10 time points here. And the blue boxes are the log intensities of the features, everything which was acquired in that farm. All the peptides, all the proteins, and so on, they just summarized. So the middle line is the median, right? The box contains 50% of the data and so on. And so what you see here is that the signal goes up in later conditions. And so the question is it biology or is it technology? It can be both, right? It is really hard to judge here. And this is why this is so challenging. So we need to, on one hand, know how the data were collected, and on the other hand, we need to build enough standards or ways to account for some of the technological variation so that we can correct for that. So in this particular case, this is actually a targeted SRM experiment which had labeled reference standards for each endogenous peptide of interest. And so in this case, MS Stats actually makes a plot like that, where we have two copies of this plot. This is for the endogenous peptides which we're interested in, and this is the reference standard. So the endogenous peptides will have the biological variation. The reference labeled standards, they're supposed to be spiked in the constant concentration everywhere. So there will be no difference between conditions. And so you see now that indeed, well, there's some variation between the standards, but not as much as here. And so what we can do then, we can equalize these boxes and then apply the same shifts to the endogenous. And so now we see that we have preserved some of the change in abundance. And now I can tell you that this was a targeted experiment where we targeted proteins which we expected to be changing. So clearly this is a biological signal and we could preserve it, but we could also account for some technological variation by working with the standards. Now, not every experiment has a labeled counterpart for every endogenous peptide of interest. So this is not always possible. Yes?
But you still, in such experiments, you prefer always to look at intensities directly. You don't look at ratios.
Exactly. And so you were here last week, right? So remember we were talking about the fact that we look on the log scale. And here again, the y-axis is the log intensity. So there's a relationship between log intensities and the ratios. And the reason why we're doing it, so first of all, we take the log so that things become more symmetric. And then we can translate the ratios to the essentially additive, right? So either differences or sums. And from the statistical perspective, working with differences, it has much nicer statistical properties than working with ratios. And this includes the fact that central limit theory kicks in sooner. It also includes the fact that you can summarize things in different ways. So we do believe that working on the log scale and working with differences is much more effective in that you can really work with more general class of experiments and understand the assumptions.
Sorry, are you focusing maybe on the intensities that you can reliably detect? Or you could always, like, is there any limit, like the minimum value of the intensity that you start to consider as a minimum?
Okay, so this is part of data processing. We will talk about it. So hold that thought. So maybe at the end of the hour it will be a little bit more clear. So the question is, well, what do we include, right? So it's essentially it's part of this, right? So what do we filter, right? So first of all, the tool they find will define, right? And then you say, okay, well, do we remove some things? I mentioned Q value, but you can also say intensity cutoff, right? What if it's low in some cases, high? You know, there are many kind of things. But let's for the moment say that these are subjective decisions which happened prior to this coming to stats. And as I mentioned at the beginning, our objective would be to minimize our dependency on this type of decisions. And so, and I will show them. Okay. But for the moment, let's just say we take whatever is given to us, right? That you can. So what is wrong? Let me just make it clear. What is really wrong is to say, let me look at healthy versus disease, and remove everything which doesn't have a twofold change, or something like that. So you don't want to filter out anything that use the information on the groups of conditions to compare. You can, because that would be essentially biasing out the results, right? You can remove things, for example, because the intensity is too low, or too high because it's close to saturation, right? So, or it has too many missing values across the board, right? But you don't want to use the information about which run came from which condition. But this is fairly subjective, and this is part of the problem, by the way, right? Remember, I just said earlier we want to minimize our dependency on this. So how can we move to that? So, okay, so this is for the normalization. And so what happens now if we don't have these standards available for every endogenous analytic function? So, well, it is possible to have internal standards, just not for every endogenous peptide, right? So we can have either spike standards, for example. It is now popular to use IRT peptides for DIA spiked as standards, or you can have some other types of standards present, or maybe, well, I haven't seen many cases, but maybe in your case you could say that there is some protein which is always so tightly regulated that you know it will not be very biological. I haven't seen many of those, but maybe in your case it is. So in this case, what we can do, we can normalize everything with respect to the single standard. So essentially, the algorithm would look like that. We take the log of the feature intensity, subtract the median of the standard, and then in that run, and then back the median of the medians, right? So we subtract the median of the standard from the run, and then add back the median of the medians. So the good thing is that standard does not have biological variation. It's independent on whether features are changing or not changing. Now, the problems here are that it only accounts for deviations which occur after we actually added the standard to the sample. So if we had some difference due to sample storage or sample provenance or something, it will not account for that. And the problem is that the standards can be quite noisy. So for example, if the standard overlaps with some other peaks, or happens to be very low intensity or something like that, we can actually do more harm than good, because we will standardize with something which itself is noisy, so we can be adding more noise than correct for them. And so what we advocate for in this case is we can use multiple standards, especially if you spike it, and then not use all of them for normalization, but use a subset for normalization, and leave the other subset as if it was a biological protein. And then after you correct it for normalization, see what happened with this other standard. If this other standard became more noisy or didn't improve, it's an indication that maybe the standard didn't work out very well. If it's improved, then it's an indication that it actually worked. So that's trying to mitigate this precise. And this is useful particularly if you have experiments with a relatively small number of proteins, or if you expect that many proteins will be affected by the stress or conditioning. So this is one option. The other option is to do median normalization. This is something that people did already in genomics, in microarrays, and so on. So the idea is to say, well, the majority of the features, and this happens when you don't have any standard, right? So it's label-free, no standards, and you would say, well, the majority of my proteins will not be affected by the stress or the conditions, so I would only expect that a small proportion of proteins will be differentially abundant, so the medians of intensities across all the proteins should be roughly equal between ones. So then the algorithm will be, okay, we'll take the whole feature and we equal it to the feature, and then back to the and it will like that. So if you have some kind of signal here, and then after normalization, we equalize like that. So it is definitely more stable than a single standard. So if single standard can be noisy, well, the median will be a lot more stable. So this is good. It accounts for all the data processing steps, right? So because this is based on endogenous proteins, you don't spike anything in. But there are also problems. So it assumes that the majority of the proteins are not affected by conditions, which so for example, here now I can tell you this experiment. This was actually an iteration curve where we have multiple replicates of samples spiked in different concentration. Of course, if we provide the medians, we eliminate all the signals. So this is actually and so we can essentially eliminate the signal by doing that. So we have to be very careful. And so the best practice for this is only using discovery experiments, maybe DIA experiments where you quantify a large number of proteins and you only expect a small number of features to change.
If I have a Silex-based experiment in DDA, then I also have a global number of features, but I also have a global standard. So what?
So this will be kind of like that. If you have global standards, right? And you equalize the standards and you apply the safe shifts. So MS Stats can do all of that.
So if you have a standard is probably still better, or would you say so?
You have to use your judgment, right? Because as I just said, the standards, they assume that everything is a constant concentration, meaning that you spiked really, like, pipetted really, really well, right? But it also means that whatever happened before you started adding standards, everything was the same. Especially if it's a large-scale experiment, you know, it may or may not be the case. So you need to use your best judgment in terms of what are the sources of variation and where they come from. Okay, and then the last part is quantile normalization. This is what I showed at the beginning. So this also comes from microarrays. So now we don't only equalize the medians, we equalize actually every single quantile. So we equalize also the 25th quantile, the 75th quantile, and so on. So this is quite aggressive. So it is known to eliminate some of the useful signals. So it's really to be used when very, very small proportion of the proteins are changing. In our practice, we would use it more for the standards, when we know that there shouldn't be any change, and we'll only apply this to non-standards. Okay, and so then the next step is, once we did that, we actually can do statistical analysis. And as a preview, well, this is what it will do. We will produce, if we have two conditions we want to compare, and this can, by the way, be complex comparisons. For example, the change between normoxia and hypoxia in one cell line versus normoxia and hypoxia in another cell line, it ends up being one comparison, which will produce one p-value. So here the x-axis will be the log-fold change of this comparison. We call it practical significance. And this is the p-value adjusted for multiple testing, right? So adjusted p-value we talked about last week. And we put it on the negative log scale so that statistical significance is up. And so now here, we're interested in things which are in the top left or top right quadrant. So they will be both practically significant statistics. And your fold change cutoff, you can edit as you wish, as long as you also account for that statistical significance. So this is for one pair of conditions. Now, if you have many, for example, you have a time course, and you want to compare time 1 to time 0, time 2 to 0, 3 to 0. So we can have heat maps like that. So here, the x-axis will be the pairwise comparisons, the y-axis will be proteins, and the color in the heat map is assigned p-value. So black means not significant, blue means significantly down, red means significantly down. So you can kind of also visualize a little bit what the trends are. Now, how do we actually get there? So how do we go from the complex designs to these conclusions? Okay, so this is really where the core of MS Stats is. And as I mentioned earlier, we are trying to work with many tools and make sure that we can process the data with whatever your favorite tool is, and that the big objective for us is to minimize the decision that we have, the dependency of the decision on which tool we use. So, well, to a reasonable extent. So let me illustrate that. Here is one experiment. So this is DDA. This is a label-free controlled mixture from the LFQ manuscript by Jürgen Cox and colleagues. And we process this with Skyline, Max Planck, and Progenitus. And here's another control mixture, DIA, processed with Skyline and Spectrum. So each plot here, the x-axis is log of the intensities of everything which was recorded in this experiment over all the months. So every feature quantified across every plot and every month altogether. So this is just a histogram of that. So what do we see? Well, we see that compare different tools, the location of the intensity of modifier optimization. So even on the kind of the numbers are quite different. For example, Progenitus is lower intensity than Skyline or Maximum. So that's okay, because we're not doing quantification, we're doing relative quantification. So as long as things are changing between conditions as appropriate, that's all we need, right? So, well, now let's take a look in terms of the number of features. Skyline gives us 200 3,000 features. MaxQuant gives us 224,000 features. Genesis gives us 56,000 features. Okay. Now, in terms of, and by feature I need to say peaks, right? So CMS peaks. Now, Skyline has 1,300 zeros. MaxQuant has no zeros. And Genesis has 600 zeros. How about missing values? Skyline has 33 missing values. MaxQuant has 38,000 missing values. And Genesis has no missing values. Now, these little bars, these are actually, this is actually part of the histogram. This is the number of values which are either exactly numerically zero or very close to zero. So take them on the box here. So clearly, MaxQuant has some kind of internal cutoff, which does not report any feature which is below some cutoff. This is why we have so many NA and no zeros. Now, Skyline does something else. It has some zeros and some missing values, but it reports some low values. Same thing for Genesis. So in other words, the tools make a number of different decisions, right? And we all agree these are reasonable tools, right? To that. But they make different decisions which have different motivation. You know, they're motivated by different experience that the developers had, and they also optimized. So Skyline was started as being a tool primarily for targeted proteomics. MaxQuant started by being a tool primarily for discovery and unique proteomics, right? So all of the legacy and the different decisions, they all combined to that we have data which have different problems. I should probably also say that when you have a nice, well-resolved peak sitting alone, probably every tool will do quite well. The biggest discrepancies are when the peaks are close to the noise level of overlap, right? So this is where the judgment comes in. And this is where, you know, some of this is subjective decision. And after that, you say, okay, what do we do with that? Do we filter it? Do we remove it? It depends, right? So what we try to do is to kind of read between the lines a little bit and try to understand what the tool really meant by putting out these numbers. And this is how we do this. So this will be one protein from this type of data. So the protein has, this is a study which has several conditions that fit the group comparison. Now each condition has multiple biological entities, multiple subjects, and each subject is quantified with multiple parts. So the pink part of this table is really our biology, right? This is our experimental design. It has the biological variation which we need to kind of, some of this is the variation of interest, what happens between conditions, and other is the user's variation, what happens between different subjects in the same condition. Now, we don't quantify the protein, we quantify every line, right? The protein will have potentially multiple features. So now to answer your question. So what I mean by feature is a peak, so essentially a combination of M over Z and retention time across all results. And the reason why we call it feature is because we want to make a kind of generic term, so it will be transition by SRM, it will be fragment for DIA, and it will be definite IM for DDA. So these are all features for us. And so for example, for SRM, if we have multiple transitions for the same peptide, this will be multiple. If we have two peptides, three transitions per peptide, we have six features. That's how we can see. Now, what do we have? We have some missing values, and the values, they are all the logs, right? So first thing we do is log transformation. So what we decide to do now is to say, okay, let us not worry about any zero small values, and essentially we'll say that if the values are below a certain cutoff, we will not trust the value. So we'll come up with the cutoff, which is, so this is that red line, this is the cutoff specific to each data set, which essentially we determine such that below this cutoff, we do not trust the values. And this cutoff is really very ad hoc, so we'll look at the 99th quantile, look at the distance between the median and the 99th quantile, because the upper tail is easier to define. And then we look at the distance between the quantile and the median, and we get the same distance on the left. So, here. And we say that you know we will replace the values, whatever, 0 and a small value. They're missing, but we will say that they're missing from Now, we don't really know this necessarily, right? Because sometimes it can be missing for other reasons, but missing for reasons of low abundance is the most common. And so we will call it NA censored, meaning that they're missing, but we know that they're stuck, as opposed to just missing. An exception is Skyline. Skyline actually distinguishes that. So Skyline will have small values for peaks which are likely to be censored, and it will have NA when it knows there is a peak, but it can't quantify it reliably. For example, when you have two peaks heavily overlapped, if you cannot record the intensity of the peak reliably, can move to NA. Or if you have a scheduled SRM, if your peak is outside of your schedule, you know the peak is kind of there, but you can quantify it. So it will be NA. In this case, we need this NA, but then we replace the small values by NA censored. So now, if we look at this data structure that we had before, well, it turns out that this structure is, yes, this is actually quite common data structure statistics. It is called a split world design, where we have source of variation from features acquired, all the features acquired simultaneously within each run, and have relatively standard models which can be used to analyze. And so what we'll try to do is to essentially adapt this model to the problem that we have. We will ignore the biology and we'll just focus on the technology. And so we will only have the yellow part of the data structure. Censored. Some of the missing values are still left potentially. And what we'll do next, we will try to summarize this data structure into a single number per protein per run in a way that accounts for censored missing values. So the way we do it essentially is a full-weight table, and you can provide this summary saying that I have missing values, but they don't missing, I know they're small. And the summary is really important. So for those of you who are familiar with that, so this is a time accelerated failure time model, where we say, okay, we have a missing value, but we know it. And so this is the first step that NSF does. So now, once we summarize this while accounting for censoring, we actually have a second step where we'll now impute the missing values from this summarization, and we'll re-summarize this again, but this time is a robust approach that also accounts for outliers. So essentially the problem that we have here is a combination of missing values and outliers. There are statistical technologies which allow us to separate one step and take care of both, but we found that numerically it takes much longer. It's not very stable, so we partition this into two steps. One is first impute the missing values, and then the second is the robust summarization, which accounts for outliers.
There might be some question about how does it define outliers?
We don't. So, okay, let's see. Hold on. We do, and we don't. So, just one thing at a time. So, well, let me show you this. So that's probably the right one. So, we have this. So we don't worry about outliers yet. We just think about censoring. We impute these values. So now we have no more missing values. So then we have a two-way table with all the data either observed or imputed. And so now what we will do, we will have a robust summarization of the row mean and of the column mean. And this is done by TUKEY MEDIAN POLISH. So you don't really say, okay, this is an outlier, I removed it or something like that. It essentially uses, you can think of this as kind of generalized medians, so that you summarize the rows with the median and you summarize the columns with the median. Here is the actual algorithm. So you subtract column median from each value, row median for each value, and iterate until there is no change. So obtain fitted values, subtract the residuals from the original values, and then average fitted values over the column. So this is the actual, so this is a very old method for a robust summarization of two tables. So in other words, it's not like we remove the outliers and then okay, fine, we want to summarize rows and columns simultaneously, so we iterate first the medians from the columns, subtract have the medians, then we take the medians of the rows, subtract and so on, right? So what's obtained is the residuals, subtract this, you obtain the feeded values. And so these feeded values will be the sum, kind of the medians over all the rows, and this is one number per protein. So let me just repeat once again. So there's several steps here. The step that we have censoring. Impute missing values in the view to the censoring using accelerated figure time model. This still may be affected by outliers, so now we can do the second summarization, which will be robust to outliers, and we obtain as the result of one number per protein per part. So why this summary is effective? So remember, I just showed you this general linear model. Turns out that this linear model can be also partitioned into two steps. First, summarizing the yellow part of this data structure, and then focusing on the big part of the data structure. So, of the data structure. So, these two steps in classical statistics are only possible if you don't have missing values and you have the same number of replicas in each condition. So, by going through these iterations, we essentially extended this beyond what we got in classical. We allow now us to put it missing values and present outcome. Because now we have the data structure which has one number per protein per run. That's exactly what we're having now. So from this point on, we can build. Well, if you want to t-test it with two conditions, you can t-test it with two conditions on this separate. But more interestingly, we can fit different models of the schema. Fair design, factorial design. Now we can be very general and also computationally quite stable.
Sorry. We want to quantify, and we have, let's say, like the limit of quantification. Where would it, like, if you say you know there's a missing value, but then small, but it might probably be below limit of quantification. Where would that fit in this approach?
Right. Well, so if it's just in one run, so it will be censored, right? And what we do, we will define again empirically what is the smallest value below which for each particular method, right? So what will be the value below which we don't see it, and then we'll say, okay, it's missing, but it's small. And the summary, well, if maybe I can draw you an example. If this is not observed, so your mean will be here, and your mean will be here. What we're saying is the mean is not here. We actually have 4 data points in the whole. We don't know the exact values, but they are sample. And so the mean will be estimated much lower than the mean of the observed data points. So now you estimate the whole change. So that's what so let's say, because when we mistake completely, we have no choice but to use the observed data. But now we're saying that missing value should be close to the close to the mean. So that's really what's more and now the action however, what happened is that one condition where things are missing, the other condition where things are present. So we can carry out statistics from that. What we will do is have the total change. From this. Again, so let's say that you have one feature, so you can essentially say that you have one feature for protein. So the base question where you would do it. staged out. But technically, yes, and we see this a lot, where people just feel, reluctant to redo their homework, but they just and that's what they do. So, see if there is a way to get to the lower type. That's one would be really nice. So we would not take the final output of max one, but we will go back several steps and we'll take some of the different outputs so that we can now we can focus on the kind of biological aspects of experimental design, understand and this illustrates what we do. So here, let's see the gray lines for conditions, right? So the x-axis is the MS1. We have three random lines. The gray lines are our LTMS features. So this is what we try to summarize. And this blue horizontal line is the line below which we don't use the values of the sensory value. So here we have no problem below the line, so this is a good product. So let's see, the green line here is, what we do, they take the features of the product on the original scale and then take the log. This is very common in tools, for example, Skyway. And of course, because it takes the sum and then the log, the summary will be above the individual value. This is one thing. You can also look at the two yellow lines. The yellow line will be robust summarization that I just described without confusing these values, and the triangle here is model, so this will be the generalized model like that. So we can just focus on the MS stats with log of sum here. But essentially, when there is no problem, there is no problem. Every method does well, p-value is large, full changes close to the right value, so we will be fine. Here's a situation where we have some interference, but in the low intensity features. Still, the features are high enough, so we trust them, but they are above our low confidence cutoff. Log of sum is not really affected by that because log is affected by high intensity features, right? So those are the most important contributors to the sum. And what we take the log. We have an interference in high intensity features. So now, cases, especially because this is a spike protein and some condition was quite a most excited about that is now we'll say, okay, how do the results depend on which tool is going to on the original scale and then taking the log. This is kind of after that because we say this downstream. So the diagrams show the number of true positives detected with the process when we analyze the data with different processes. And we see that consistently the agreement between tools is much higher if the summarizes by accounting. And this means that already some of these choices are somewhat mitigated. Right? And our computers are more reproducible across data processing tools. If we essentially don't take this that reports that the tools output literally, we have to try to give it processing appropriately. And the reason why it's useful also because we see things that the data processing mass accuracy, we don't get to see it in our reports anymore. It's already kind of abstracted away. But what these tools don't see is how much variation there is between reports. And we use this additional information to help make these decisions. So this is another one for TIA. So these are also 3 sets of controlled mixtures acquired with TIA. This is analyzed with log sum. This is analyzed with MS stats. Same thing, right? So we have much more consistency in MS stats than if we process this with log sum. And you know, we have done more than that in terms of evaluation. Like yet to see a case where we do worse in terms of reproducibility compared to just taking more. So this is to say that, you know, we can, by looking into all this process, we can help make our results less dependent on some of the choices, which we make subjective. And going back to our work, now that we've done all that, we estimated various components between the replicates, right? And we can use this to design experiments, in particular, do the sample that we discussed last week. So I have another part I want to talk to you about, but before that, to summarize that MS Stats is available in many ways. So it's available on Bioconductor. So we roughly have 200 to 300 unique IP downloads to Bioconductor every month. It is also available as an external tool in Skyline, so you can work with this in Skyline through the graphical user interface. You can use R for that. It also has 15,000 downloads. It's very exciting. We also have a dedicated website where you have the news about the latest releases, you have documentation, you have example data sets, and very importantly, we have a group where you can post your questions about different topics. Okay, so now let's go back to the question that we had before. Okay, so what do we do with filtering, right? And how the data processing and filtering matters. So we did a lot of work also trying to understand the limitation of this stuff, because even though we help make the results more reproducible, we don't claim that we solve all problems. And we wanted to understand to which extent data processing matters and to which extent we can mitigate some of the choices. which you will actually look, so those of you who are staying for it, so you will actually look at this case at the end of the week. So the problem with the spiking experiments is that it doesn't really have the full biological variation. We have the same background, we just have some protein spiking. And it's more interesting to look at the data sets which actually have the real biological variation. So this is the manuscript from that we had in collaboration with the ABRF. It studied yeast samples subjected to osmotic stress. The data were collected at 6 time points, 3 biological replicates per time point, so on the SciEx instrument. What is interesting about this experiment is that, first of all, the response of osmotic stress to evaluate the results of this study, but also this was still in the early days of DIA, and so the investigators did additional work to develop DIA assays carefully. And so we did 2 analyses by Skyline, and by me, but by we I really mean Brendan and Bina, who did most of the work. And Brendan will be here starting on Wednesday. I'm very excited that he will be leading this part of the program. So there were 2 analyses. So the first was, okay, let's just keep all peptide precursors and take top 6 fragments per peptide 4 quantification. But at the same time, what they did was have a separate refinement experiment where they took the same biological material and collected ADA. And the idea was to see how reliably we can quantify the fragments of these activities. It's always the same sample. Every intermediate. And so in this case, we only selected peptide precursors which were detected in at least 50% of these refinement plants. The idea being, if I take one sample, I do it 8 times, and I can't quantify the half of the times. It is not a good assay, right? So I will remove consideration. I will only work with the fragments which I can quantify reliably as refinement plants. And also taking it for consideration, which have coefficient of variation less than CSO. So essentially, this is a criteria for filtering. So we will say we'll filter away everything which was observed unreliably in this kind of refinement experiment. And then we did additional work, so we processed this with Skyline, Spectranode, DIU Pyre, and we did different type of filtering. So you will have a chance to experiment with that towards the end of the week. So what did we find? So first of all, the data processing, right? So how this filtering strategy contributes to the analysis. Well, so here this is using everything. Here this is using only the subset of analytes which have low CV. So this is the number of proteins. Of course, if we filter out things which are not reliable, we will have fewer proteins, right? So we lost 4,000 proteins in this experiment. And now if we look at the number of differentially abundant proteins, always comparing the time point 0 to different time points, so we see that here, the number of proteins which are differentially abundant goes up dramatically, and then it drops down and goes back up. Whereas here it goes less up, but steadily and more consistently up. I would argue that, again, we don't know exactly what's going on in this biological study, but I would argue that this is more biologically plausible than this. This is likely having more random variation. So if we now look at the particular pairwise comparison, so we see that there is some overlap between using everything versus using low CV, and there is some substantial overlap between that. And this is one particular protein from everything versus low CV, and so we see that this type of strategy allowed us to filter out experimentally some of these things, so we still have an outlier. This is an outlier that MSS will have very limited time with, so we will be able to handle that. And this may be a little bit more difficult. And so we see that because of that, for this particular protein, With all of this interference and so on, MSTAT says that this pairwise comparison is borderline significant. After using kind of better process, we see that there is no change. Right? So clearly, good data processing methods, right? So even though we can mitigate some of the outliers, we cannot solve all the problems. But at the same time, looking, well, here's another protein. Also, so this is now the opposite, right? So keeping everything resulted to, gave us too much noise. The filtering allowed us to be more sensitive to detecting the fold change. So it can kind of go both ways. Again, this is much easier for MSTAT to deal with this in terms of outliers and disadvantages. And then we processed this with different tools, as I mentioned. And we see that clearly there's a lot of variation. So this is skyline low CV, and the same protein with speculum and DIA umpire. DIA umpire, I need to have a disclaimer, it is not designed for this instrument. So it performs more than it would perform on more kind of higher mass resolution experiments. So it does noisy, but it doesn't do justice. This particular data set doesn't do justice. Spectronaut has some variability here, and we see that we have different types of interferences here, but MSTATs could mitigate some of this in other tools. And now in terms of overlap, so we don't know what the true change is, so we cannot do exactly the same Venn diagrams as in the spiking experiments, but there is a well-known pathway which is important in response to that, to this stress, and so we see that in terms of the consistency of overlap of proteins which are regulated, which are in this pathway, we are higher than if we just use the law of sound summarization. So, in other words, good data processing helps, right? But at the same time, we can mitigate things to our certain extent.
So if this were not a DIA, but for example, that SRM experiment with spiking standards, so we would have ratios, would you say that doing the CV cutoff or ratios for a particular peptide would be enough, or would you still look for the data processing, the manual data processing step? Would you still look at intensities?
Well, so if you did something here, so you would have refinement run. Clearly, for SR, you do a lot of work designing your assays, right? And looking at CV and limits of detection, and all of that. This is a really important part of that. So I would hope that by the time you're ready to do the actual biological study, you will be confident that your assay is doing appropriately. At that point, I would just collect data. Let's say you have label reference standards. What I didn't mention here, I didn't have the time, but MSTAT handles labeled references as part of the analysis. So you don't have the ratio, you have log intensity for the endogenous, log intensity for the reference, and MSTATs would do, because, well, going back to our discussion next week, in this case, the run is a block, right? So you have two features, right, endogenous and reference in the same block. So MSTAT will use the blocking strategy to look at the differences on the log scale as opposed to comparing the ratios. And it's useful again because if you have missing value, if you have outliers, you will be doing better with MSTAT than if you just calculate the ratios. So that's the idea. Okay, and so now just the very last part, and this is the work by Sunken side, who's sitting there, so I want to acknowledge his contribution. So we decided to look a little bit further and say, okay, can we actually do so this filtering that we said, okay, 20% CV, like 50% missing values and so on, this is still quite subjective. Can we replace this type of manual decisions with some more objective and more automatable decisions? Not just depend on outliers, but can we actually eliminate some of the features based on the more objective and more automatable steps? And so we're working with the same data set. So there were different ways of processing that Sunken considered. So one was keeping a data set which has everything, but have the Q value cutoff, meaning that if we have one feature which has a bad Q value, we'll just one LCMS peak which has bad Q value. We'll eliminate this big wall. So now the data set becomes very sparse because it has many missing values corresponding to the peaks which we remove because they have bad Q value. Now 50% means that we keep everything, but now if we have a feature across the right where a couple of things become missing because of the Q value, and then we do the same thing, but also using this low CV based on the refinement files. So this is most permissive tool with different types of filtering, and this is most stringent based on low CV. And so this is some example proteins from here. Well, first of all, you can see that in terms of number of differentially abundant proteins, the data process steps clearly make an impact, right? So they change how many proteins total we have and how many differentially abundant proteins we have. And so this is some examples of the proteins. This is full sparse, meaning we kept all the features, we didn't consider refinement runs. We will have many missing values because we do Q value filtering. Here we have everything, but we'll remove features with many missing values, so it's a little bit more clean. And here we only work with features which survive this refinement run filtering and Q value cutoff, and we see that we have even fewer noisy features. And so TUKEN developed a procedure which allows us to start with this or with this and arrive to this in a way that doesn't require refinement runs, essentially. And we learn from the data that some features are too noisy and have too much variation, eliminate them without having to connect refinement runs for every experiment. And so there's a procedure. I will kind of not go into great details in the interest of time, but we'll look at how many missing values are appropriate, or how many missing values are too many, what is the appropriate extent of variation in the proteins. We can define outliers, we can define noisy features, and I will just show you how this works. So if I have a noisy protein like that, the black line is the summarization with MSTAT, which is already somewhat robust with all the features, and in yellow, this is the summarization which will be obtained after we filter out some of the noisy features. And now, why does it matter? Because we can say, okay, if we start from noisy data, if we don't have the luxury of making correctly refinement runs, and if we don't know what's Q value type of strategy to use, we use this procedure to essentially minimize our dependence on the results of these decisions. And so here we look at comparison of two time points. If we use all the features with MSTAT, which is already supposed to be quite reproducible, so this is different data processing decisions and the overlap in the differentially abundant proteins. And this is now if we use this automated procedure to filter out noisy features, and we see that our conclusions do not depend as much on which filtering we use. So I hope it makes sense, right? So we just spent a lot of time saying, okay, we have this refinement runs with CV, we can filter by Q value, we can filter by missing values and so on. Despite the use of MSTATs, we can have different results. So what TUKEN is saying, all of these choices that we make, by filtering, sparsity, and so on, they make less impact on our conclusions. Essentially, we filter out those features, which make it their way into the report. And so this is an example. This is from the Navarro controlled mixture. So this would happen if we take either all features. By the way, just to take the top 3 features, not the most important, but most high intensity features. And so the blue line, this will be the top 3 summarization, which clearly is affected by outliers. And so in procedure by TUKEN, we can filter out these outliers, and we will have the summarization which is closer to the true values. And in terms of agreement between different tools, so we can use all the features, we can use top 3, we can use top 10, and so on, or we can use the procedure which filters noisy features out automatically. We see again that this maximizes the reproducibility between data processing and different tools. So in other words, kind of the more recent work procedure, which decides what to filter out. And then all of these various filtering strategies, they have less impact on our conclusions than if we did. So let me stop here, and I need to take the entire group. So Mina, Zunhe, Ting, who are here, are the main contributors to MS Stats, and we also have Sarah, who is here as well. She contributed to another part, which I hope to talk about tomorrow. So this is really a big effort by many group members, and I'm very grateful for that. I also need to acknowledge the ABRF IPRG group. A lot of this work was done in collaboration with Brendan McQueen in Michael Costa's lab and with TH Zurich, and I'm very excited that Mike and Brendan and Ruth